all the factoring techniques that we've talked about, plus there's a couple of extra ones that we're going to discuss here in just a moment. But this is a good, it says general strategy. This is a good summary for us of how we ought to attack a factoring problem. Okay, remember that to factor something means to write it as a product. And so we're going to go about that in a methodical way, each and every problem that we get. It shouldn't be, hey, I'm just looking at it and, oh, I'll try and figure it out. It ought to be where if I throw a problem your way, you realize, oh, okay, I know what to do right out of the gate. So now that you guys have this on your screen there, what we can do is we can, first of all, always look for a GCF. That's the first thing that's up on our list, right? So I tell students all the time, if you're going to write a list of factoring techniques, GCF is at the top, okay? Then we look at difference of squares. That's where it's a binomial times its conjugate, okay? Then over here, as far as the trinomials go, we've either got a regular trinomial, a magic method trinomial, or a perfect square trinomial. Okay, perfect square trinomial is what they've got right here. If it's more than 3 terms, we talk about grouping. And then for today, when we look at these bottom 2 right here, the sum of cubes, whoops, pardon me. What did that do just now? Let's do Control Z. Bring it back. Yeah, there we go. When we look at these bottom 2 right here, oh, there I go again. I think I'm leaning on my trackpad while I write. And that's the problem. Those are 2 new techniques, okay? And we're not going to spend a great deal of time talking about the sum of cubes and the difference of cubes. Typically, these are Algebra 2 techniques. But I want you to go ahead and write those 2 formulas down just so you'll have them in your notes for ready reference, okay? And then also, you see up above there where it says sum of squares. Again, that's an Algebra 2 factorization. It says sum of squares do not factor. That's a lie. They do not factor over the real numbers. Once you get into Algebra 2 and you learn about the complex number system, a sum of squares will factor as well, okay? But those 3 up on your screen right now are all 3 Algebra 2 factoring problems, okay? When I talk about a perfect square, we went through last week and we discussed our list of perfect squares, right? Like 1 squared all the way up through 20 squared. When we talk about perfect cubes, we ought to know 1 through 5. 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125. We ought to know our first 5 perfect cubes. And that's not the first time this year that I've said that. But really recognizing sum of cubes and difference of cubes, I tell students all the time, it's just memorize the template and plug it in. Okay, memorize the template and plug it in. This is the template. This is how we set up. Whatever A is, I plug it in wherever I see an A. Whatever B is, I plug it. So like if B were 8, if this was A cubed minus 8, what would B equal? What number when multiplied by itself 3 times gives you 8? 2. So A cubed minus 2 cubed, in other words. So my B value would be 2. And everywhere I see a B in the formula, I'd let a 2 sit there. And we'll see an example of one of these here in just a minute. Yeah, you got these written down? Right, good? All right. Now, up at the top, not to scare you guys, but up at the top in this lesson, in this section, this is where it gets a little bit tricky. Okay. The section right here is we're not going to learn anything brand spanking new, but we're going to put into play all of the factoring techniques that we've been going through up to this point in like 2 or 3 factoring techniques in one single problem. All right, so it gets a little bit tricky, but if you look at it as a method, you'll be all right. Now, goodness knows I don't want you guys to write down all this stuff over on the left side of your screen, okay? This is just, I pulled it from the text, but it sort of is a step-by-step checklist for, like if you were going to call somebody like a factoring troubleshoot Geek Squad kind of call. They're going to take step 1 and they're going to walk you through it. Right? You know that's what they do. When you call somebody that works on the Geek Squad and you say, hey, my computer won't work, they whip out a checklist and they start at the top and they start troubleshooting. One thing right after the other. Now, the good Geek Squad guys, the good computer tech will have some intuition after a little bit of time talking to you about the problem. Will have some intuition to where he could diagnose it probably a lot quicker. That's like a good doctor, you know. And so this checklist, I'm going to sort of say that's great as a backup, but what I want to teach you guys is factoring intuition. Okay? What is intuition? You know what that means? Quentin, what's intuition? Yeah, very good. It's a feeling about something. Okay? You've ever heard the expression mother's intuition? Okay, if my wife and I are sitting in the kitchen chit-chatting, and then she thinks, wait a minute, something's wrong. And we go to the back of the house, and one of the kids has hurt the other kid, and they're being all quiet about it and whatnot. She had mother's intuition. She didn't know for sure, but she had a feeling about it. When you factor, I want you to factor intuitively, using intuition. In other words, don't just go to this rote memorization of step-by-step checklist. Look at the problem and think, I think I know what to do here, and then do it. All right, number one, example one. You look at the first thing on our list always is a GCF, okay? And Lewis, tell me, what does all three of these terms have in common? What do all three terms have in common?
5x squared.
Yeah, very good. A 5x squared. Okay. Almost called you Grady. George, what do I have left over now when I take out that 5x squared from each term?
Squared x minus.
Fabulous, George. Fabulous. And what he did, again, remember, fellas, was that mental division. He just mentally divided each term by 5x squared. So Lewis says, hey, take out the 5x squared, and then George did it. Do I stop there? Of course not. I told you guys these are going to be challenging problems, right? The temptation is to do one technique and then stop, but we can't stop, okay? Joey, what else should I look for now? I got my GCF taken out. What do you think, Joey? What's in the parentheses? What kind of polynomial? Very good. It's a trinomial. So I know it's not difference of squares, sum of cubes, difference of cubes. That's binomial stuff. I know it's not grouping. That's how many terms? That's 4. So this is a trinomial. Now, the quadratic coefficient is 1, so I know it's not magic method. So this is a regular, what I call a regular trinomial. And Luke's going to tell us, what do I do with this -6, Luke? All right, that's okay. James? I'll give you a hint. I put a line under here because I'm about ready to do like 1 times -6, 2 times -3, 3 times -2. Come again? Now, multiples of 6 would be like 6, 12, 18, 24. Yeah, we want to find a pair of factors. And Drew, what special pair of factors am I hunting for? The one or the pair that adds up to equal that linear coefficient. Y'all pay attention to that. Remember, with our regular factoring technique, our regular trinomials, our goal is to find the pair that adds up to that linear coefficient. And in this case, you guys would overwhelmingly tell me what? 3 and -2. Quentin, 6 and -1 would tally up to 5. So if that linear coefficient were 5, you'd pick that pair. But we want to pick this pair right here. So what we're going to say is, let me scooch this over just a little bit. I got my GCF out front. Don't throw the baby out with the bathwater, right? And then we got what? X plus 3 and X minus 2. It's like a reverse FOIL problem. So I could check my work, right, Jack, by doing what? Yeah, just multiply, FOIL the binomials, and then distribute the GCF, and you should get back what you started with in black. Back in black. Good AC/DC song, Alex. You ever heard of the AC/DC? Some Aussie rock band. Oh, yeah. If you've ever heard Thunderstruck, that's like their most popular song, but they got one called Back in Black that's pretty tight, too. All right. So to those of you that I was kind of questioning about, you pull the GCF out, and then what do you do next? Brush up on your regular trinomial factoring. That one's the easy one, right? Where we just look at that constant term. We find 2 factors that add up to the linear coefficient. We've got to practice, practice, practice. Okay. Example 2 is a binomial. Is there a GCF, Joe Edwards? There ain't nothing in common between a to the 6th and 64. No common factors. So the next thing I look at on my list would be, since it's a binomial, I'm going to see if it's a difference of two squares. Now, interestingly enough, when we talk about perfect squares, I know that 64 is a perfect square, right? 8 times 8. 8 to the 6th is also a perfect square. Reed, what would you write as far as its two identical factors? What times itself equals 8 to the 6th? All right, that's okay. I'll give you a hint. It's not a times a, because that would give me a squared. It's not a squared times a squared, so that would give me a to the 4th. It's not a to the 5th times a to the 5th, because that would give me a to the 10th. It's not a to the 4th times a to the 4th, that would give me a to the 8th. Ah, that a process of elimination. See what I did there? Okay, so you're right. It's a to the 3rd times a to the 3rd. How could I have gotten that, Grove, a lot quicker than just kind of guessing and checking? What could I have done with the original 6? How do you get from 6 down to 3? And oh boy, cut it in half. Cut it in half. So if I've got a to the 100, okay, Jake, split that up. Is that a perfect square, by the way, a to the 100?
Yeah.
How do we know it is an even exponent? Split it up. A to the 50th times a to the 50th, okay? So a to the 222. Is that a perfect square? Yeah, it'd be a to the 111 times a to the 111. All right, are you ready for this? What about a to the 2n, where n is some integer? When? A to the n times a to the n. Now, I know I did that verbally, and that's a really abstract concept, so let me write that down. Excellent job, Quentin. A to the 2n, where you're told, hey, n is some integer, some number like 2 or 3 or 4 or 5 or 6. It doesn't matter what n is. We could split that up. Ooh, and I like how I'm seeing people writing this down. We could split that up as a to the n times a to the n. That's an example of one of our popcorn exponent rules, whereby you just add the exponents when the bases are the same. What's n plus n? 2n. Okay? That's a good honors level kind of concept that we need to shoot for here. Okay? Is that something is a perfect square if its exponent is even. And if I tell you that n is an integer, 2 times any integer is what kind of number? An even number. 2 times an integer is an even number. Now, I just gave y'all like 3 or 4 lines worth of goodies to have written down. I hope that you got that pencil moving. Now, back to what we've got here in green. Okay. How do I factor out, what's my template for a difference of 2 squares? Y'all know what I mean by template? How do you set the table? James? Okay, and do what? Like what's the form of my answer going to look like, generally speaking here? Are there going to be some parentheses? What kind of terms? All right, so a couple parentheses. How many terms in each of those parentheses, Charlie? So they're binomials, okay. Are they the same binomials? Are they different binomials? Is there a relationship between those two binomials? James was kind of telling me what they were going to be. I'll write them up. A cubed plus 8, a cubed minus 8. Lewis, you remember what the relationship is called?
I just remembered that one was positive and one was negative.
Just remembered one was positive, one was negative. These are called conjugates. Y'all have heard that word in here before, right? Conjugates. Write down in big, fat, bold letters, the way that the difference of 2 squares factors out is that binomial times its conjugate. I believe I gave you one like this on your test. I said x squared minus 9, something like this. You might have had this show up on your exam or something like that. I think maybe. That would factor out as x plus 3. X minus 3. We've talked before that if it was like x to the 4th minus 81, how would you split that up? X squared plus 9, x squared minus 9. But wait, Coach Morgan, you just told me x squared minus 9 is a difference of 2 squares. So we'd what? We'd factor it again, wouldn't we? So we wouldn't just stop with the 1. This is why these problems are hard, because you're tempted to stop right off the get-go. Yeah, difference of 2 squares factors out as a binomial times its conjugate. Yes, the difference of 2 squares factors out as a binomial times its conjugate. And remember that word conjugate, fellas? Just means like a plus b, a minus b. It's a binomial, like Lewis said, where the terms are the same, just the operator in the middle is different. It's a really important concept. You'll see that again a buttload of times in Algebra 2. Quentin. Great question. I was hoping somebody would ask that question. Quentin, you're 2 for 2. Way to go, bub. All right, so first of all, highlighted in yellow is exactly what we had on the line above, right? Just basic difference of 2 squares factorization. So Quentin's question wasn't, hey, why'd you do that? We all should understand that's difference 2 squares factors out as a binomial times its C word, conjugate. Quentin's question was, why didn't you do something similar to what's in green? Why you didn't factor out the sum of squares? Now, do you remember at the beginning of class, we had that little chart? I'm going to zoom out. We had that little chart. And does anybody remember what I said about the sum of squares and how our Algebra 1 textbook says sum of squares does not factor? Louder. It does factor, just in Algebra 2, okay? So we cannot right now, because we have not studied complex analysis, we can't break up that x squared plus 9. Now, typically what I like to do, and we're not done with the original problem up here in green, but we're just kind of taking time out. What I typically like to do when somebody asks Quentin's question, which every year that question gets asked, it's a very important question, is I like to say, okay, if you think this should factor, go ahead. How would it factor? And so typically, what do you think students will tell me? They look at the yellow one and they think, okay, so it's not going to be binomial times its conjugate. That would make for a negative on the inside. So what do you think students typically tell me? Yeah. Like in this context, maybe what? X plus 3 times x plus 3. Does that seem reasonable? Okay. Check it real quick. Foil it out real quick. X plus 3 times x plus 3. Of course, we're going to get x squared. And of course, we're going to get 9. And you're thinking, hot dang, all right, yeah. But if it's a FOIL problem, I can't ignore the OI. I can't ignore the outer, which gives me 3x, and the inner, which gives me another 3x. Unlike the conjugate, where the outer and the inner have opposite signs and therefore cancel each other out, here they've got the same sign, so we would just say plus 6x. And this was how we factored out perfect square trinomials last week, right? Remember, I think on Thursday when I was gone, you guys watched a screencast to that effect. So it's not going to be x plus 3 times x plus 3. And similarly, it's not going to be x minus 3 times x minus 3. If it was x minus 3 times x minus 3, the same deal would be over here. It'd be negative 3x on the outer, negative 3x on the inner, and therefore negative 6x for that middle term. It would again be a PST, neither of which shows up right here. All right. The sum of squares does not factor out like you think it would. And you don't have the chops yet to learn how it would factor. I'll go ahead and show you how it would factor out, though, because I'm sure curiosity is just nibbling at you right now. X squared plus 9 factors out as x plus 3i, x minus 3i, where I is the basic imaginary number square root of -1. Again, that's algebra 2. We probably take 3 class periods to discuss that in an algebra 2 class. So you're looking at it like, huh? Don't worry, you'll figure it out one day, okay? But suffice it to say, Quentin's question is very important. It does not factor out, and therefore, we would just stop right there. Now, back to the problem in green. Does the problem in green factor out a little bit further? Say yes. Yes, it does. What is interesting about a cubed plus 8 or a cubed minus 8? I used that specific example when we were looking at our chart again back at the beginning of the lesson today. What is a cubed plus 8 and a cubed minus 8? Jack Candiato. The sum of cubes and the difference of cubes. Now, everybody, I asked y'all to write down those formulas, right? You remember what those formulas were? This one would have been a plus 2, a squared minus 2a plus 4. The second one would have been a minus 2, a squared plus 2a plus 4. Again, you don't have to take it that. Why aren't you writing that down, Alex? Dadgummit. You don't have to take it that far, fellas. Okay? You'll learn how that goes in an algebra 2 kind of class. When? Absolutely, my man. So those are just 2 examples of our sum of cubes, which I'll highlight in yellow. Here's the sum of cubes. And our difference of cubes, which I'll highlight in blue. And again, not to teach you guys an algebra 2 lesson here. I think y'all are very capable of doing it. It's really just memorize the template, memorize the formula. But ask yourself the question, what is my quote A value and what is my quote B value? Well, A is just A. That's pretty straightforward. What did we say our quote B value was on that one? 2. You ask the question, okay, well, what is being cubed right here? And you say, oh, that's 2 cubed. And then you plug in, everywhere you see an A, you plug in an A. Everywhere you see a B, you plug in 2. So like in the template, where the template had, I'll write it in black, A plus B, A squared plus, minus, AB plus B squared, right? That's exactly what we did. Everywhere we see a B, we plug in a 2. Everywhere we see a A, we just, left it as A because that's what it was right there. All right. Not too shabby. The trick on example 2, again, remembering not to stop until we had fully factored everything. And the trick there was recognizing, perfect square, difference perfect squares. I factor out as binomial times as conjugate, and then take it a step further with the difference of cubes. Let's look at example 3. Oh, and I got plenty of room for example 3. Ooh la la. All right, example 3. Tiago, what's the first thing I should always look for? And the greatest common factor, Jack McBee, between 200, 120, and 18? 18 does not go into 120, nor does it go into 200. Stop thinking about GCF and just think about CF. What's a common factor that strikes you about all 3 of those? 2. When you take out 2, you're left with 100, 60, and 9. 9 and 100 don't share any common factors, so 2 is it. Okay? And then what else do we recognize as common between all 3 of those terms? A T. So 2T is our GCF. Did you ever think that algebra would have so many daggum letters floating around? 2T is our GCF. All right. Andrew, you want to tell me what's left over when I take out my 2T?
100R squared, 60RS, and 9S squared.
Y'all know what I smell? What do I smell? Smells like a perfect square trinomial to me. Anybody else smell a PST? Oh, yeah. How do I know something is a perfect square trinomial? George, what must the first term be? Not even. A perfect square. Is the first term perfect square, class? Yes, it is. 10r times 10r. Again, this goes back to last Thursday. Hope you watched the video. Joey, is the last term, this is our second check on our list, is the last term a perfect square? How so? 3s times 3s. Now we get down to the nut cutting, as they say, when gelding horses. Not that we're gelding horses up in here. Okay. What is my third check that I must run? What must I make sure? James Jacobs?
You multiply the 2 that you circled and then double on.
Very well said. I'm going to say that a little bit louder in case guys online didn't hear it. When you saw me circle both of these guys, multiply the two things that you circled together, double that result, and if that's what's in the middle, then you got yourself a PST. Now here's the $5 question. Drew, how does a PST factor? How does perfect square trinomial factor? I'm going to keep my 2t, by the way, on the... Dadgummit, I'm leaning on my thing again. I'm going to keep my 2t on the outside. What's the template for a perfect square trinomial? Remember? Rats. I'll help you. It's a binomial squared. A binomial times itself. And can we fill in, Alex? Can we fill in that binomial? Psst, I circled everything you need. 10 what? 10r, hold on. 10r plus, that a boy. 10r plus 3s. All right, we got to brush up on our PST factorizations. Yes, no? All right. Now, that one was a GCF and then a PST. Both of those, by the way, I consider bread and butter factoring techniques. They ought to be wham, bam, thank you, ma'am. Real down and dirty, real quick and easy. Just get after it, okay? The trick there is that there's a couple factorizations both in that same problem. We're going to skip the grouping one. We're going to jump down, because I'm almost out of time, to example 5. And I want us to practice. This one is a PST, excuse me, a GCF, got my wrong acronym there. It's the greatest common factor. Hopefully it's obvious what's in common. And then the result is going to be a little magic method issue. And I want y'all to try that one on your own, because we hadn't done magic method in a few days. So take out your GCF, and then let's apply the magic method. Give you about 30 more seconds. All right, you take out the GCF, that's easy, that's step 1. The result is 10x squared plus 11x minus 6. Now, where this one differs from the previous ones is we had one of them that was, quote, regular trinomial. That ain't the case here, because the 10, that quadratic coefficient, is jacking my style. And it's not a PST because neither the first term nor the last term are perfect squares. So this is a telltale case for magic method. Remember how your magic method works? I'll run this through real quick. We let 10 disappear. We want to make it an easier problem temporarily. I'm going to use a different color. We multiply 10 times that last term. We pretend like this is our problem. How would this problem factor out? It's kind of like what I asked, I think, Luke and maybe Joe or James or Quentin, somebody over there earlier. We look for two factors of negative 60 that add up to 11. Those factors are 15 and what? -4. Good. Then the 10 comes back. It had disappeared. Now, like magic, it comes back. We kill off any remaining GCF between 10 and 15. That's a 5. Between 10 and 4, that's a 2. So our final answer is going to be 2x. Don't forget the GCF of 4y on the outside. 2x plus 3 and 5x minus 2 with the 4y on the outside to boot. And how do you check your work? You FOIL it out. Okay? We've got to practice factoring. We got to become factoring masters, don't we? Because everything we do over the next couple months is gonna have some tie-in with our factoring abilities. Okay? So that's our last lesson on the basics of factoring. We're going to start using factoring tomorrow in some applications. In the meantime, live Jesus in our hearts. All right. Thank you, fellas. Y'all did a great job today. Keep it up. You boys online, y'all take care. Thanks again.